Hey guys, welcome to Unit 8, Stoichiometry, and oh, what fun we will have. This is a really neat unit because it combines a couple of the things that we've talked about earlier. We talked about predicting products and balancing equations, and in the last unit we talked about being able to convert grams to moles and moles to grams and chemical ratios and that sort of thing. So in this unit we'll put those important concepts together to be able to predict how much of a product that we can make in a chemical reaction. And this is a fun unit, I think one that you'll enjoy, and let's get started on it. Okay, some general concepts here. Let's start with the definition. Stoichiometry is the skill of predicting the amount of product that can be produced or the amount of reactant needed to produce a desired product. That's chemical math. And so you can kind of think of this like making a cake. Let's say that your mom sends you to the store and she says, I want you to get the ingredients for 2 cakes. And so you read on the cake mix that you need 2 eggs and a cup of milk. And so for 2 cakes, you're going to need at least 4 eggs, and you're going to need 2 cups of milk. Well, you would get a half gallon of milk, or maybe a quarter gallon of milk, and a half a dozen eggs. And so you're going to have some milk and eggs left over when you make your cake. And so this is some of the types of calculations that we can make with chemical equations and being able to convert from mass to moles. And so we're going to put those together so that we can figure out how much product that we can make, how much of the leftover reactants that we will have, or if we're short on something, when the reaction will stop. And so as we go along, this sounds really complicated, but we're going to lead you through it step by step, and you'll be an expert by the time we're finished. Okay, let's talk a little bit about the tools we'll need. We already have all the tools, we just got to put them together. You'll need to be able to convert moles to grams, or grams to moles. We've covered that in the last unit. You'll need to be able to predict products and balance equations. That's in the unit before the last one, in unit 7, chemical reactions. And so you already know how to do that. And then you'll need to be able to use the chemical equations to make conversions. And you already know how to do that. You just don't know you know. So we will go over that, and not to fear, we're going to teach you everything that you need to know to be successful. Okay, so we are going to do some of these conversions, and we're going to start with the easiest type. And I always think that it helps to have a flow chart before you start these things. I think if you refer to the flow chart, it will help you from getting lost or confused about what kind of problem that you have. And so let's take a look at this flow chart. It may look a little bit familiar to you because we've already converted grams to moles, right? And in the last unit, we went from moles to particles. And so in this unit, we're going to be going from grams to moles, and then we're going to use the chemical equation to change from one chemical quantity to the other, and then eventually we'll turn those moles back to grams. So from grams to moles, just like before, we're going to use a molar mass off the periodic table. But when we change from moles to moles, instead of using the periodic table or Avogadro's number like we changed to particles before, we're going to use the balanced equation in the coefficients to change chemicals from one chemical species to the other. And then once we get to moles, then we can do a number of different things there. We can change it to grams, or in the next unit we'll talk actually about changing those moles into volumes of gases as well. Okay, so we're going to start with these moles to mole type of conversions. And our first problem here says how many moles of carbon dioxide can be produced from the complete combustion of 20 moles of octane. Alright, so you'll notice here that we will need to write a balanced equation before we can even start. in the problems that I give you in your worksheets, I have done this for you, but I thought it would be a useful exercise to review those skills that we learned back in Unit 7. So let's do that. We will write a balanced chemical equation. So how many moles of carbon dioxide can be produced? All right, so that's going to be a product from the complete combustion of 20 moles of octane. So we've got octane first, C8H18, and to combust anything, you need oxygen. And it tells us that we're going to produce carbon dioxide, and our other product is always going to be water in a combustion reaction. So now we have our skeleton equation, one that is not balanced, and we will balance the equation. Remember, in combustion reactions, we always balance carbon and hydrogen first and leave oxygen to the end. So if we have 8 moles of carbon on the reactant side, we'll need to put an 8 here to get us started on our product side. If we have 18 moles of hydrogen in the reactant, 9 times 2 will give us 18 moles of hydrogen here. All right, so we've got hydrogen and carbon balance. Now we need to work on our oxygen. So we have 8 times 2 is 16 oxygen atoms in carbon dioxide, and we have 9 oxygen atoms in our water for a grand total of 25. All right. So there is no whole number that we can multiply by 2 to get to 25. And so we're going to use our fraction trick that we introduced in the last unit here, and we'll put 25 over 2. Now, if we could leave it like that, it would be balanced, but you need a whole coefficient number. So to get a whole coefficient number, we're going to multiply through by 2 everything to get whole numbers. And remember, if there's nothing there, it's assumed to be 1. So 2 times 1 will give us 2. 2 times 25 halves will give us 25. 2 times 8 will give us 16. And 2 times 9 will give us 18. And so now we're balanced. We started off with a pretty hard one, didn't we? Okay, but you can do it. All right, so now we know we're solving for moles of carbon dioxide, and we're given 20 moles of octane. I always like to write it above my chemical symbols to kind of keep me straight so I don't grab the wrong coefficient when I'm going from moles of one thing to moles of the other. And it's a moles to moles type of problem. So for moles to moles, we only have one step or one conversion. So let's write down our 20 moles of octane, and we're going to have one conversion. We're going to change one chemical to the other. I'm trying to color code this for you to make it a little easier to see. So we have just one conversion. What goes on the bottom of our conversion factor? Well, whatever we're starting with, right? So moles of C8H18 will go on the bottom. And what are we solving for goes on top, which is the moles of CO2. So when we got moles to moles here, moles to moles, we use the balance equation and the coefficients off that balance equation. So what goes next to the CO2? Well, 16 goes next to that one, right? And what goes next to the octane would be 2. So now we have 20 times 16 divided by 2. And I get 160 when I did that. So you would end up with 160 moles of CO2. The moles of octane cancel out, and we're left with moles of CO2. And that's what we were asked to solve for. That was our X. So we're in good shape there. All right, so let's think about that number for a minute. We've got 20.0. So there's 3 significant figures. Our answer here as written just has 2 significant figures. So we are going to have to write that in scientific notation to get our two significant figures. So it would be 1.60 times 10 to the second moles of carbon dioxide. All right. Very good. Very good. All right. Let's see what the next problem is. All right. The next problem says how many moles of sodium cyanide are necessary to react with excess sulfuric acid to produce 45.6 moles of hydrogen cyanide. Okay, so we know that sodium cyanide is going to react with sulfuric acid. So those are our reactants. So let's write them down over here. So we've got sodium cyanide and sulfuric acid. Okay. I once was a chemist, but now I am no more. For what I thought was H2O was really H2SO4. Think about that one for a minute. All right. And so here we know that sodium is going to react with sulfate and hydrogen is going to react with cyanide. +1, -1, +1, -2. Okay. So sodium sulfate +1, -2 plus HCN +1, -1. So don't forget to crisscross your charges here. So that's going to be Na2SO4. All right. So don't get impatient here. You got to balance it before you can start. Like I said, I'll give you mostly these balanced equations. So if I put a 2 here next to sodium and then a 2 next to hydrogen cyanide, we will be balanced. All right, so moles of hydrogen cyanide. Hydrogen cyanide will be our X here. I have to put it down here, X moles, right? And 45, how many moles of sodium cyanide? Oops, almost got mislabeled here. So sodium cyanide is what we're solving for. It's a little different than the last one. We're actually solving for a reactant in this one. And we're given 45.6 moles of hydrogen cyanide. So we're given here 45.6 moles of that guy. Okay. So you always write down what you're given. So we're given 45.6 moles of HCN. And this time we're back solving we're solving for the reactant needed to make the product. So here, what goes on the bottom of my conversion factor? Well, I'm starting off with moles of HCN. So moles of HCN will go on the bottom. And then we're solving for moles of NaCN, or sodium cyanide. All right, so let's look at our balanced equation now, since we're moles to moles, right? So we got to look at the balanced equation and pick off the coefficients. So sodium cyanide gets a 2, and then hydrogen cyanide gets a 2 also. So it's a 1-to-1 ratio. So moles of HCN will cancel, and we'll end up with moles of sodium cyanide, NaCN. And this is an easy one, right? It's going to be 45.6 moles of NaCN. Very good. How did you do? Could you do this? You got lots of practice problems to give you a chance. So what you can do is you can work the practice problems, the moles to moles problems now if you'd like before we go on, or you can go on and then come back and refer to these notes when you work them. The next type of problem that we're going to do is a mass to moles type of problem. Okay, so now we are going to do some mass to mole type of calculations. Our flow chart will remain the same, and the procedure is just one more step. So we're kind of building our repertoire of chemical calculations here. And so let's work a problem as an example. It says how many moles of potassium sulfate can be produced from the reaction of 38.9 grams of potassium nitrate with excess calcium sulfate. So our reactants here are going to be potassium nitrate and calcium sulfate, and then we are going to use those to find out how much potassium sulfate can be made. So we'll start off with a balanced equation. All right, so the first step would be to write down what we're given, which is 38.9 grams of potassium nitrate. And we are given grams, and we're asked to solve for moles of another chemical, the potassium sulfate. So we're asked to solve for moles of this guy, and we're given grams of this guy, which is 38.9 grams of that guy. So those are the two chemicals that will be involved, and we have two steps because we've got to go from grams of one chemical to moles of the same, and then from moles of one chemical to moles of another chemical. So we'll need two conversion factors here, moles to moles there. All right, so let's get started on it. Whatever you have in terms of a unit in a chemical will always go on the bottom of our conversion factor so that it will cancel out. So we got grams of potassium nitrate here, and we're going to go to moles of potassium nitrate. Whenever you go from grams to moles, it's always 1 mole. And then let's label this good, KNO3. So we'll have moles of KNO3 on the bottom, potassium nitrate, and then moles of what we're solving for on top, which is moles of potassium sulfate. So now we just got to fill in the values and solve. So the first one will need the molar mass, because when you go from grams to moles, you need the molar mass. So let's do a molar mass of potassium nitrate. We have 1 mole of potassium in the compound, 1 mole of nitrogen, and 3 moles of oxygen. Potassium's 39.1 grams per mole, oxygen's 14 grams per mole, and oxygen is 16 grams per mole. So here we have 39.1, 14.0. 3 times 16 is 48. Double checking myself here. 48. You add all those up, you get 101.1. Okay, so there is our molar mass of our potassium nitrate. And so now we're going to go over the mole bridge, moles to moles. So we need the balanced equation to do that. So moles of potassium nitrate, we have 2 moles of potassium nitrate for every 1 mole of potassium sulfate. Remember, there's nothing there. It's assumed to be 1. All right, so now we multiply across the top and divide by the bottom. So it's 38.9 times 1 divided by 101.1 times 2. So when you're plugging this into your calculator, be sure to keep the order of operations straight, or you might get the wrong answer. And when I do that, I get 0.192 moles. Okay, very good. So we have another problem coming up here, another mass to moles type of problem. So what I would like for you to do, we'll use the same balanced equation. I'd like for you to go ahead and work this one, and then we'll work it together. So pause the video here, work the problem, and then we'll work it together. All right, hopefully you did that. So we're starting off with 106.7 grams of calcium nitrate. So we are desiring a grams of our product, and we're asked how many grams of the reactant, how many moles of the reactant that we need. So we're going to go from grams to moles, and moles back to grams this time. So a very similar problem, just a little bit different approach. So we'll still start with grams on the bottom of whatever that we're given, just like before, calcium nitrate. And we still need to change that to a molar amount so we can change chemical species. And then we are going to go to moles of the reactant. So for every 1 mole of calcium nitrate, or mole of that product, we'll need, I said 1 mole because it is here, calcium nitrate is a 1. Be sure to emphasize that one. And then we're going to go to moles of calcium sulfate. And in this case, it's going to be 1 mole of that one as well, because there's no coefficient in front of the chemical in the balanced equation. Okay, so now we just got to figure out our moles of our calcium nitrate. So let's do that. So we have Let's do that in red. Why don't we? So we got 1 mole of calcium. It's 40.1 grams per mole. And then we've got 2 moles of nitrogen, which are 14 grams per mole, which will give us 28. And then we've got 2 times 3. 2 times 3 is 6 moles of oxygen. 6 times 16. And 6 times 16 is 96. And when we add all those up, we get 164.1 grams. And that will go on the bottom. Alrighty. So now we just multiply across the top 106.7 times 1 times 1. Divide it by 164.1 times 1. And if you do that, you get 0. We'll do this in black because that's the reactant. 0.6502 moles of calcium sulfate. Okay, very good. And so in the next slide, we'll do problems that are moles to mass types of problems. You'll find that those are, again, two-step problems, but they start off with a mole-to-mole conversion and then moles back to grams. Okay, so now we have some more problems, and we have moles to mass types of problems. And this one, we are solving for grams of water that are produced when 40.5 moles of pentane are completely combusted. And to save us a little time, I went ahead and wrote a balance equation out. So this one we are solving for grams of water, and we are given moles of pentane. And this one is 40.5 moles of this guy. All right, this one's a little different than the ones that we have been working, since we're starting with moles and we're going to go to grams. So on this one, we'll go from moles to moles first and then moles to grams. So let's write down our given. You always write down the given, which is a number in a unit, and that's always your starting place. And if you can do nothing else, you can convert that to something else, right? You got moles, so moles will go on the bottom of our conversion factor. And since we're going to moles of another chemical, moles will go on top as well. And moles of what we're solving for, and we're solving for water. All right, and then we can go from moles to grams next. So moles of water per grams of water. Okay, so let's pull off our coefficients. We'll use the balance equation and the coefficients again. And so moles of water will be 8. Moles of pentane will be 2. So we have a 8-to-2 ratio there. And then to finish up, for every 1 mole of water, we have so many grams of water. I have to look at the periodic table for that. So for every 1 mole of water, you have 1 gram of hydrogen. So, but we have 2 moles of it, so 2 times 1 will give us 2. We only have 1 mole of water and 16 grams per mole for that guy, and we have 18 total grams here. So now we have 40 times 8 times 18. We multiply across the top and divide by the bottom. And so grams of high quality H2O. We've got a little bit more significant figures than we need here. So we only have 3 in our problem. So we'll round there. So we'll say 2920 grams, 2,920 grams of H2O. By significant figures. Okay, so there's that one. Let's do another one. Wow, because they're so much fun. That says, given the equation above, how many grams of pentane must completely combust to produce 24.6 moles of carbon dioxide? Okay, so let's erase some of the stuff up here just to help us with a point of reference on our problem. So grams of pentane are what we're solving for here, and we're given 24.6 moles of carbon dioxide as our starting place. So 24.6 moles there of that guy. So this time if you can think of it, we're going from moles of the product to grams of the reactant here. So 2 steps again, just a little bit different as we go. So let's write down what we're given. We're given 24.6 moles of CO2. Always write down your given. and write a conversion factor, because you know you're going to convert it to something. And then we know we're going from moles to grams, so we're going to have one more conversion here. Forgive my squiggly lines. Okay. All right, so what goes on the bottom of the conversion factor? Well, whatever you're starting off with, moles of CO2. The unit and the chemical, but not the number. And so we're going to have to go from moles of that guy to moles of something else. So moles, and we're solving for pentane, C5H8. So moles to moles. And then finally moles of pentane to grams of pentane. So moles to grams. All right, let's do our moles to moles conversion. How many moles of pentane do we have? Well, we have 2 moles of pentane. 2 moles of pentane here. How many moles of carbon dioxide do we have? We've got 10 moles of carbon dioxide. And now we need to do our moles to grams conversion to finish this out. So we got C5. Carbon is 12 grams per mole. And hydrogen, how many hydrogens we got? We got 8 hydrogen moles there times 1 grams per mole there. I believe that's 60. 5 times 2 is 10. Carry the 1. 5 times 1 is 5. 60. So we got 68 grams per mole there. Alrighty. So let's do our calculations. 24.6 times 2 times 68 divided by 10. 5H8. Notice here that I'm rounding to 3 significant figures. Okay, so that ends our moles to grams type of problems. In the next slide, we will be doing grams to grams, and we'll also talk about a concept called percent yield and limiting reagents. So looking forward to seeing you in the next recording, where we will do more chemical math, learn more chemistry, and have lots and lots and lots of fun.